Hello everyone, this is a short tutorial on how to create a dynamic spline, and that will actually looks really nice if you have every parameter set it up properly, and it will utilize some of the dynamic stuff, but it's not that complicated. So let's just create a spline chain like this, and let's give it a spline IK. So let's go to rigging, skeleton, create IK spline handles, and you just need to use the default setting, and let's click on the root and then the top, and here we have a spline IK and we have a curve and IK handle. Okay, let's name it spline curve. And let's just leave the IK handle alone. Maybe we just need to hide it because it's never going to be used. Anyway, let's select our spline curve. And as you can see, if we move the curves, the whole chain moves. And if we isolate it, select some of its point. And if we go back, you can actually using the point to change the shape of the skeleton chain. So all you have to do is use some dynamic to drag this spline curve, and let's select the curve and go to FX and particles, and here we found a soft body, and let's just create use the default settings, just make soft and create, and that actually create a spline curve particles. And if we isolate these spline curve particles, you can see I actually have 4 particles here, and that 4 particles actually is actually exactly on top of the vertices of our original spline curve, as you can see here. So if we go to here, you can see the particle is right on top of the vertices. Okay, cool. And if we select the particle and let's go to field and solvers, create a gravity field, and let's give it more time, and let's play the thing. You can see as the particle drops, the spline curve drops along with it, and that's actually the idea of this dynamic rig, is utilizing this particle system to make the spline curve looks like dynamic. But we're not going to use gravity field or any other field. But if you want, you can try create another field like turbulence, and you play it. You can see as the particle moves, the spline moves along with it. And if you select spline, you can see it's actually every vertices is following the particle, and they always be right on top of each other. And that's actually a very good thing we can utilize. So let's just delete our turbulence field, and let's go back to the particles. Okay. And before we do anything, let's create a nervous circle, and we can use it as a controller. So let's name it controller. Okay, and then let's select our spline curve. And the way we utilize its dynamic is not going to use field, as I said before, and what we're going to use is a go function in the particle system. So let's select our original spline curve, duplicate it, and let's delete the particle system underneath it, and this new spline curve will be called spline curve go, and we make it the child of our controller. Oops. So if we move our controller, this spline curve go moves with it. And if we utilize the go function to make all the particles trying to stick with this new curve, and then it will have a dynamic effect on it. And what I mean is very simple. Let's try to do that so you can see it clearly. Let's go to node editor. We have our controller here. We don't need its shape, so let's just delete this node and let's drag in our particle. Okay, and let's drag in our go curve as well. Okay, and let's select our curve particle and select our go curve, and let's make them a go first. And you don't need to change anything here, just need to reset settings, change the go weight all the way up to 1 and create. And now they're connected. As you can see, they're actually connected like using the workspace connected to the Go geometry. And what actually happens is that now when we use interactive playback and we drag the controller, you can see everything follows. It's because all the particles in this particle system is trying to stick or go to this new spline curve go. And because we set the weight all the way up to 1, we try to create that relationship, and you can actually change it here, so they're kind of like always stick together. There's no shifting at all. So now if we change the value of the go shape down a little bit, like 0.7, and let's try to play it again, and we move the controller, you can see there is actually some dynamic happening. But unfortunately, all the particles having the same go weight as 0.7, which we define here. So they are now moving like exactly like each other, and that's not what we want. We want is we want to have those 4 particles listed here. Let's just select them, and let's change the render type from point to numeric, so you can see there are 4 of those particles which has the index from 0 to 3, and we want them to have different go weight, so they behave different. We want the one which has an index of 0 has a full weight, so it will always stick with our curve. But we want the second one, the third one, and the fourth one have different go weights, and their go weights will be gradually smaller from 1 to 3. And in that case, this one always, this 0 one always stick to the curve. This one has an index of 1, we will try to stick with a very big weight, and then the third one, which has an index of 2, will also try to stick with the curve, but it has a smaller weight, so it's kind of like waving around with a much bigger offset, and then the third one will kind of linger in more than the ones before it. So this is the basic idea. So all we want to do, or all we need to do now, is try to let them to have different go weight. But right now they are the same, so we need to go to the per particle array attributes, and actually the go pp is the attribute we're going to need. So let's right click on the go pp, and let's see, we create a ramp. Okay, and now the ramp is controlling their individual weight, which I mean the individual go weight, and when they evaluate the ramp, they use the array mapper, and the parameter actually controlling where to find the actual value for the different particles is by this v coordinate pp, which means if this v coordinate pp gets a value of 1, which means it will read the position 1 here, and it will gets a value of 0, and that value of 0 is actually the odd value of pp to that particular particle. So in this case, this parameter is controlled by age normalized. The v coordinate pp is controlled by the age normalized. So their age will determine their v coordinate pp, which means their v coordinate pp, or which means their final output will be controlled by their age. And because their age are all the same, because they born at the same time, and they dies after 5 seconds, after 1 second, because if you have that, you have this ramp created, it will always get a constant lifespan mode. But what we want is a different value out of different particles. So lifespan is not different. So we don't want to use that. So let's change our lifespan mode back to live forever, and we don't need this connection from the age normalized to the v coordinate pp. We need another value, which is a different value on the different particles. In that case, we can have a different sample point on this ramp, which means we will have a different out value pp, which means we have a different goal weight. Okay, so what should we be used to control this v coordinate pp? Well, every particle have a variety of different parameters, and there is one parameter we can utilize here, and that parameter is their math. And right now their math is all the same. And let's go to the component mode, and let's try to select the points. Should be able to select them. Okay, now you can select them. Maybe we need to tweak some of the parameters of particles. You need to enable this, so you can just select them in the component mode, and then let's go to Window, General Editor, Component Editor, and in the particles you can see now they all have a mass of 1, and because we can change them in here, so we can have a different value for every different particles. So that's what we can utilize to control the v coordinate pp. So let's do that. For the first one, we give it like a 0.001. You cannot give it a 0 because a particle with a mass of 0 is not, it cannot be calculated, and it will give you an arrow says that. So you need to give it at least something, if not 0, but very close to 0. And the second one will be like, let's divide the whole value from 0 to 1 3 times. So we have 0.333, 0.666, and eventually 1. So now if we select point 0 or particle 0, you can see it has a mass of 0.001. Particle 1 has a mass of 0.33, and point 2 have a mass of 0.66, and point 3 has a mass of 1. So now they have different masses. And if we shift drag our shape nodes of the particles right onto the array mapper. Oops, let's do that again. Oops, sorry, I need to get a little closer. And we'll be able to bring up the connection editor. Oops, do that again. Okay, cool. And now let's go find math, which is right here, and let's use math to control the v coordinate pp. Okay. And what this does is, for example, Maya will evaluate every particle individually, and when Maya is evaluating point 0 and particle 0, it gets its math, which is 0.001, and it uses that math. Remember what we connect from math to the v coordinate pp, and the v coordinate pp gets a value of 0.001, so it's looking for a area from 0 to 1, and you're looking for that 0.001 position, which is its position, and it's actually very close to full white, so it has a value very close to 1. So that value of very close to 1 will be outputted from the output value of pp, and that value will be directly connected to go pp. So what particle 0 will get is a go pp value, or its go weight above 1, almost 1. So if we're evaluating particle 1, then we get a different value. We'll get a different go pp value is because particle 1's mass is around 0.33, so we're getting a value around this area. So it's a little bit smaller than full white, so it's kind of like 0.6 or so. So now this particular particle's go weight is around 0.6. So then this one, they all have smaller and smaller go pp values. And if you want to check that, you can select all of the points, and let's go to Window, General Editor, Component Editor, and let's take a look. So we are actually having them displayed here, so you can see the point 0 have a mass of 0.001. It has a go pp almost 1, and then particle 1 has a value around 0.6, and particle 2 has a value around 0.3, and eventually 0.3 have a value of 0. So its go pp 0 is completely floating, it's not following anything in that case. Okay, so now if we try to play interactively, you can see you drag the controller, you can see there actually has some effects. Because 0.3 has actually no go, so it's kind of like going on its own way. I don't know where it's going, but you get the idea. So we cannot give it a value of 1. It's a value of totally 0. It will floating around. So there are a couple of different ways we can do that. In the array mapper, we have a min and max value. So if you change this min value to 0.5, then every value get evaluated, and then output will be first be put into this range from 0.5 to 1. So it's kind of like squeezed the value you can get from this ramp 1 into this into these two values. So in that case, if you get a value of 0, it actually will be 0.5. So now our particle 3 will have a go pp of 0.5. So let's see, if we play this again, you can see now it gets what we want. It's actually a very flexible follow through, and has this kind of a nice real dynamic overlapping in it. And because we are using Go, it's actually very light. It doesn't need that much of calculation, and it's totally doable and affordable to create a kind of like fake dynamic thing happening here. And it works fantastic. It will never break. Okay. And now if we want to have something changed, like if we want to change how much the overlapping is, we can always go back to our main controller, right? Then let's give it a add a new attribute, and let's call it thickness, or anything you think would be proper for you to describe how much overlapping you want. Let's create OK, and it has a value from 1 to 0 to 1, and let's connect our controller's thickness to the mean value. And the bigger the thickness is, like if we change this all the way up to 1, to very, very big value, and if we play and try to drag, the follows is very, very close. because it always gives you a value of above 1, almost 1. And if you give it a value of like 0.7 and we play again, you can see now they have different values. How cool is that? Okay, I think that wraps up of everything I need to explain to you, and then I can just try to create something polycube, and let's make it bigger so we can give it a rig, and so you can see the result. It must be looking really cool. Okay, let's select the joint and our cube, and let's go to skin. Let's go to animations, rigging, skin, band skin, and yeah, expand the skin. Just give it a little time. I don't know why my 2016 is kind of a little bit slow on this process, but it works. And let's see the results. Look how cool is that? Well, maybe we have we need to tweak the weight a little bit, but you see the results. It's fake dynamic, or it's actually a real dynamic. It's a lot cheaper than real dynamic, and it's actually much stable to utilize. Okay, well, thanks for watching, and if you have any questions, please leave a comment, and I will see you next time.